couple more minutes just to make sure everyone's in the Zoom. While we're waiting, does anyone have any questions from last time? Open up the chat window. Sorry, the neighbor's dog is fine. Chat. There we go. There's a chat window. Okay. Okay, so we'll go ahead and get started. I think pretty much everyone is in that we normally have here. So today the main two topics are going to be looking at the architecture for a new robot project. This will be sort of the default architecture. If we have time, we'll talk more about how we've been building our own architecture. And then the second hour, we'll be looking at sensor fusion. We'll review some of what we did for the camera, and then I'm gonna let you guys lead the creation of the sensor fusion algorithm for the LiDAR system. And I'll also point out, I found a bug last night in our current sensor fusion algorithm that we've been running on the robot. So we can talk about what that bug is, and we can fix that. But before we get started, there was one thing from the last session that we didn't get to, which was clusters. And then I also realized that we never really covered the comparison palette at all, but we kind of used it. So I'm just going to go through those two items at the very beginning. Are there any questions before we start? Awesome. Okay. So the comparison palette isn't super exciting. We've sort of been using parts and pieces of it, but I haven't really gone through it in detail. So what we've been using is we've been using the select block. But also inside of that, we've got you know, the greater than and less than and equal sign comparison. So anytime you need to make those sorts of logic, those sorts of comparisons, you go to the comparison tab. Probably the other thing that's useful is these two blocks. So we've got a max and a min block. So you can put in two numbers into this, and it will tell you, it will return which one's the maximum and which one's the minimum value. And the other useful block that's shown here is the coerce block. So what this one does is you have three input terminals. You have a lower limit, an upper limit, and the number that you're checking. And so if we put in, let's put in a number, and we put in a lower limit and say that the number shouldn't be allowed to be less than 0. And we're also going to not allow the number to be greater than, I don't know, 30. And so if we look at that output, since 42 is larger than 30, it's going to max out at 30. And so if we then type in something smaller than 30, you know, if we typed in 29, then it will push through our actual value that we typed in there. So that's a pretty useful block. The other thing to note is that if you right click on it, you can choose to include or not include the lower or upper limit. So if you include them, it will work for 30. So this is more important for integers, like if these were integers instead of floating points. If we didn't include the upper limit, then you couldn't have a number larger than 29. If you did include the upper limit, you could have a number of 30. So it's just like whether or not you include the range and the allowable values. And for floating points, it's not a big deal. For integers, it could be a difference of a value of 1. You can get to that just by right-clicking on it. So nothing too special. I just wanted to make sure y'all were aware of what kinds of blocks were in the comparison palette. Are there any questions about the comparison palette? Okay. So the thing that we didn't get to last night was clusters. So let me see. So we looked at arrays last night, and we said that arrays were essentially lists of values. The other restriction for arrays is that you can only put in values with the same data type. So if I grab a floating point number, I put it into the array, and then I try and grab, say, a Boolean value, it's going to give me a broken wire. So the array isn't going to allow me to have values with different data types stored inside of them. Clusters, on the other hand, do allow you to do this. So we go over to the cluster palette, and we take so instead of it being build array, what you're going to have is bundle for a cluster. And so if we try and do the exact same thing for a cluster, we aren't going to get any broken wires. And you can actually see that at the inputs of the cluster, we have the data types listed right there at the beginning. And the way you then extract the values from the cluster is with an unbundle. And so the cluster wire is always a thick pink line with sort of these white dots in the middle. And at the output of the cluster, when you do the unbundle, you have the inputs in the same order that they were bundled together over on this side. You can basically think of a bundle as, literally a bundle of wires. Like if you were to zip tie a whole bunch of different wires together, it wouldn't matter whether or not some of them are power wires and some of them are sensor signals. You can stick them all together at once. The reason that you might bundle stuff is, essentially for neatness, particularly if you need to take a whole bunch of wires into a sub-VI. And we can talk more about sub-VIs later, but basically sub-VIs are functions or blocks that you create. If you want to take multiple values into those, the pink wire can be useful. The cluster can be useful. I'll show you that the LabVIEW architecture that is used for the robots uses clusters really extensively. And so I'll point out some examples there of clusters. The other thing that you can do with clusters, and I'll show you an example here, I can load it up maybe, is you can build an array of clusters. So if for whatever reason you do need to have multiple types of values in an array, you can take a build array and you can put clusters as the input to the array. And as long as each cluster that's going into it has the same exact format. So it's, as long as they're all a floating point and a Boolean, you can build an array with it. And that gives you some other options. And the example I'll show with clusters and arrays in a second is how we do the text-to-speech for the error messages. Let's see if I can. Oh, I can't mute Dr. B because he's the host. Are there any questions so far on what clusters are? What is one problem that you might see with using a cluster if we have a whole bunch of inputs? Like if we've got 100 inputs in the 100 different wires in the cluster. Any thoughts on what might be a problem with that? So if you're using your piece of code, if you cluster everything over here, and it's way over here on this side of the screen, and you try and unbundle stuff on this side, do you think how hard do you think it might be to remember what each wire is and where each wire should go afterwards? So that can be a bit of a challenge. There is a solution though. So the bundles that I grabbed here are just like the regular unbundle and bundle. There is also options for bundling by name. So if we click the bundle by name, it'll give us 3 things this time. And we grab, I'm just gonna grab a floating point number, a Boolean, and I will also grab an integer. And then if we go to
pepperoni.
unbundle by name,
so I found some of the discrepancies.
Yeah. Connect
This part,
you can see that we have a gray line.
Notice we got this one on the 7th.
An error
that
won't let us run this code.
That part. But
And that's
this
because
part was $79.
we need to actually, it's going to require that we name these wires.
I didn't see it or didn't pay it.
So
It was
if you right
different.
click here and say create
It's
constant,
715.
well, that 70 has been there for, if you look at all the olds, there's a whole bunch of old ones.
I know, but there's multiple 70s. They're often
we
70s.
found,
Oh,
So I missed
Dr. B, can you mute your mic?
but I went back and double checked this date. And if you notice, we got this on the 6th, which means
Hey, Dr. B, can you mute your mic?
because the way they show up in here are separate
so you'd already paid it.
things. Part of it I had, so I just paid the $79 today. So this one is done. There's a couple that I can't, there is nothing that shows up online at all for a couple of these, and I'll just have to call tomorrow. Because this account number, if you go either here or here, this number doesn't show up anywhere. When I go to this online and enter the information, it doesn't show up.
We're about to get Dr. B's
When I look in our building stuff, it doesn't show
So
up.
if anyone
So
wants
just
to
call them
order
tomorrow and
anything,
see if there's a digit.
they should do so now.
Right. The other one is Family Clinic, and there's no way to do that online, and it doesn't come through here. So I'll just have to call that one. And the other one is
Hey, Dr. B!
I bet he's muted us.
it's not done through here either, so I'll have to call them.
I'll bet he's muted us.
Yeah, right. Right.
Oh, can you mute
There we go.
You can hear it.
Oh, mute's not muted.
Oh, there we go. Okay. So looking back at the bundling by name, it actually won't run the code until we provide names for each individual wire. And the way that we do that is a bit odd, but essentially you copy the constants of the data type that you want, and then you drag them into the box. And then you do the next weird thing, which is you right-click on each of these, and you add a label. So we'll call this one A. We'll call it Boolean. And we'll call this one okay. Now the other thing that has to happen is it's still broken. You need to click with your mouse until you get the little finger, and then select the correct item from the list. And then you can do that same thing on the unbundle side. There are some other ways that you can create this constant, and I haven't done it in a while, so I'd have to go back and look. That allows you to save this and share it with other programs. That if you use one type of cluster really frequently, you can basically load in a saved version that you don't have to recreate it every time. But I need to go back and review that. And the other nice thing about this is now if you take the help and you hover over the pink line, you can actually see the name for each of the individual wires and their data type. So it gives you that information pretty quickly. Are there any questions on clusters before we move on to looking at the robot architecture? I can see you talking, Amelia, but I can't hear you. So great question. So Amelia asks, what would be an example of when we would use clusters? We'll see some really good examples here. I'll show you one example now, and then we'll see some more examples when we look at the robot project, actually. So that's one of the reasons I want to cover it today, was that it'll be in the robot project. But here we can show you an example of how we're using it in our code. So I do think I have to pull that project from repository. So the code I'm going to show you guys is the dashboard code from this year. And we are using clusters for the text-to-speech, to the error messages that Karen plays. So if we open that. That's exciting. Okay, so in the dashboard code, what we have is a whole bunch of errors that Karen can say. And for each error, we need three things. We need what Karen should say, which we are storing in this pink constant, which is a character string. It's a string constant. We also need the trigger. So what thing has to be true in order for Karen to say those things? And then the number of seconds that Karen should wait until she repeats the error message. And for each error, we need those three items. And we also have a lot of errors. And so the portion of the code that reads in the errors needs them to be in an array. Now, we can show you that later. It's a little bit more complicated. We can talk about that maybe in another session. But it needs to be in an array. And what we had originally actually were 3 separate arrays. One array for all of the messages, one array for all of the Boolean triggers, and one array for all of the time delays. And we would pass all 3 arrays individually into the error builder sub-VI here. And that worked, but once we started getting a whole bunch of error messages, it became really hard to see basically what corresponded to what, like what message was corresponding to what trigger, because you had this long list and you had 3 of them, and it was sort of hard to match them up. So we changed that so that we bundle the 3 pieces of information that you need together for each individual error message, and then build the array afterwards. Does that work as an example for you, Amelia? Awesome. Okay. So we will now go on to, unless there's any other questions, does anyone else have any other questions about clusters? Okay. So we'll go on to looking at the default robot code. There's more examples of clusters in there. It's pretty frequently used in the robot code. So, okay. So the way that you create a new robot project is, instead of hitting blank VI, you go ahead and click on FRC RoboRio project. You can name it whatever you want. There's no restrictions. You can have spaces. So we'll just call this default robot project. You might want to move it to a specific location. So I'm going to go ahead and move this to the training folder so that it's all together. And then it's also going to ask you to type in your team number. In the past, you had to be a little bit careful about what your team number was. If you had multiple robots in the same room with the same team number, you wouldn't be able to connect to them simultaneously. That's no longer the case. As of at least last year, all of the robots in a room can have the same team number. The only time that you will need to change the team number on a RoboRio or in the robot project is if we're going to like Robo Rodeo or something. We've got 2 of our robots on the field at the same time, and then they'll need separate team numbers. But if we're just doing development in the shop, you can just go ahead and put in 4265, and that'll save people from having to guess what team number you used for your robot. The next options that we've got down here are the different types of default projects that you can open. We use this default arcade drive as our base. There are 2 options here for sort of tutorials for learning LabVIEW. I honestly have never clicked them, so I haven't really played with them at all. And then your other option is this command and control option. This is a significantly different way of controlling the robot than how we've been doing it. Mars does use the command and control system, as far as I know. There are advantages in terms of the amount of bandwidth and computation time that you use while you're running the robot, but it does also make it a little bit more challenging to debug. And I think there's a little bit steeper of a learning curve. I'd also say that we've mostly been able to mitigate the CPU challenges with some custom VIs that we've developed that make our code behave somewhat similar to the command and control architecture, but in the normal architecture. So right now, I'd make sure that you're set to arcade drive before you hit finish. And then it'll take a second while it makes the project. Okay, so what you have now is a LabVIEW project. And you can think of a project as a collection of files. And so this is the Project Explorer window. That project also exists on your hard drive. So if we go into the training folder and into the default robot project folder, these are the files that are associated with that project. And the file that sort of bundles them all together is this LV proj file extension file. And then these are all of the sub-VIs or functions that are associated with that project. And then there's some additional files that get generated with that project. It's really important that any files that you want in your project are also located inside of this folder. Otherwise, when you sync the project back up to Git, you may miss some files, and when someone tries to download your project, they won't be able to open it because they'll be missing files. Are there any questions on creating the project yet? I'll go into more detail as to how to add files and stuff in a second. Okay. So if we sort of turn our attention back to the Project Explorer, this target here is the RoboRio on your robot. And the name that's in parentheses is what the computer is going to use as the network address in order to talk to the robot. The default network address that LabVIEW uses is what's called a dynamic. It's basically a network name. So instead of it being an IP address, it's a name that's supposed to be associated with a network address, with a network IP address. That relies on what's called the DNS server on your computer to work properly. And when it works properly, it's great. You don't have to worry about it, and it just works. My experience has been that the DNS servers on most laptops, particularly school laptops, really don't work properly. And so leaving the dynamic name in here will often lead to like sort of very hard to diagnose connection problems with the robot. And so what I suggest is that you go ahead and put in the hard-coded IP address for the robot. And the way you do that is you right-click on the target and you say Properties. And then under General, you can type in, instead of the DNS name, you can type in the IP address. And let me find that real quick. So on Git, there is a repository called Critical Documents that you can also download. And one of the files that's in the Critical Documents folder is this robot networking text file. And this file has a whole bunch of information in it about what all the IP addresses are for the different parts of the control system, how to connect to the robot to send information with the tether cable, how to configure the robot project to handle the autonomous plays, all that kind of stuff. And so the one that we're looking for is the RoboRio IP address when we are untethered. And really this should probably be edited to say untethered or tethered with an Ethernet cable. And then this IP address is if we're tethered with the USB cable. So the IP address that we want is 10.42.65.2. And then see, now you can see that has changed in the parentheses. Does anyone have any questions about the robot IP address or where to find this document with all the IP addresses listed? Okay. So now that that is set, we'll sort of have to figure out a way where we can demo connecting to a robot. There's not really a good way for me to do it without a robot here. So We'll have to think about that because I would want to go over that at some point with everyone. So for now, we'll skip how we connect to the robot, and we'll just look at the code. So what we've got is this robot main. And if we double click on that file, it's going to take sometimes it takes a longer time to load it. Actually, it'll do pretty fast, but sometimes it'll take a while to load because there's actually pulling a lot of different pieces of code together. And if we go into that, what we see is the default robot code that FIRST provides all of the teams. And what we see are some things that happen at the very beginning, things that happen throughout the entire time that the robot is on. And if you look, we actually have a case structure where we have the different modes that the robot goes through. So you've got when the robot is disabled, you have when the robot is in autonomous, when the robot is in teleop, and when the robot is disconnected from the field. And in each one of these cases, you've got more sub-VIs that each do different things for each of those different modes. We typically don't put any code in these case structures. And if we have time tonight or in a later session, I'll show you how ours is set up. And I'll show you where we put the code. But FIRST puts code by default inside the case structures. The other set of items that we have are pieces of code that are running in parallel. And so these are things that also have loops. So this is a loop, and then these pieces of code also have loops, and they're running simultaneously in parallel with this whole loop. So the code that is actually controlling the robot is either running in these case structures or in one of these parallel loops. But before we can start controlling the robot, we have to do a whole bunch of initializations. And so if we go into the begin VI, what we see are initializations of devices. And so for example, we have to initialize the joysticks. And so the way that works is we need an open statement, and each different type of device has a different open block. And where you get to those is if you right click and you scroll all the way down to the WPI robotics library, this is where you start to see blocks that are specific to the devices that we're using on the robot. So if we go to the joystick palette, you'll see this open block right here. And it has one input. Basically, you have to say which USB port that joystick is plugged into. And the output of the open statement is a cluster. And that cluster contains, in this case, it actually just contains one thing. It just contains the USB number. I'll show you in a second that there's other clusters that are put out by the open statements that are more complicated. Now, the next thing that you need is you need a way to refer to this joystick by name later on in the code, because you might have multiple joysticks. And so if you want to pull values from a specific joystick, you need a way to refer to that joystick. And we do that with what is called a refnum. And so you also need to do this refnum set, which takes as an input the cluster from the open statement. And then it also requires a string constant where you're going to name this value. And what that allows you to do is then anywhere in your code, you can put down a refnum get. And if you name this the same thing, then the cluster that comes out of this will be the same as this cluster. So it will essentially retrieve all of the values in this cluster and bring them out here based on the name that you type in. Are there any questions about opening things and refnum names? So one of the challenges with reference names is that if you've got, you know, however many motors that we have in sensors this year, it can be really difficult to remember these names. And these names have to exactly match each other. Otherwise, you're not going to pull the correct value out when you think you are. And so I'll show you guys, we haven't really talked much about storing things in variables. But one of the things that we do is we store the ref num names in variables, and essentially it allows us to select the names from a drop-down list. And when I show you our code architecture, you'll be able to see that. And that way, instead of having to remember the name that you typed in, you can just select it from a drop-down, and that reduces the chances that you're gonna type in the wrong name. If we look over here, we've got a very similar thing going on with the motors, where you also have an open statement, in this case for PWM motors instead of the CAN bus. You have to select what type of speed controller that you're using. And you can also input things like whether or not to invert the direction of the motor. And if you hover over that pink line, you can see that cluster contains a whole bunch more information. So this pink wire contains all of these individual wires. And so that is everything from the PWM port number here. It might also be the protocols that the PWM controller needs for that specific motor. So some of you know that one of the last things that we worked on before we had to stop meeting was getting the linear actuator to work for the cow. And we were really struggling to get it to go its full range. And that has to do with the specific PWM settings for that device. And those aren't recognized by FIRST right now. So like, you know, the linear actuator doesn't show up in this drop-down list. And so we're having to look at the documentation and to see what the correct PWM settings are and manually input those in order to get it to communicate properly with the linear actuator. One of the other things that you can do while you're opening devices is you can configure them to do different things. So if we look at a more complicated open statement, like if we went to the open statement for a Talon SRX, we would have an open. In this case, this requires that we go to the CAN bus. So the ID number here is the CAN ID. We will need the get ref num, sorry, the set ref num. Just like before. And then we'd also need to name it something. So we'll call it Talon, or Talon 1. But there are other things that we can do. So if we went to set neutral mode, for example, we could connect pink line to that first. And let's see if I can clean that up real quick. Sorry. What this one does, oh, I lost the help, is set whether or not the motor is going to go into brake or coast mode. So if the motor is in brake mode, if you stop giving it a command, it's actually going to switch on the magnets in order to lock the shaft and keep the shaft from rotating. Whereas in coast mode, if you stop applying a command signal, if you tell it 0 power, it's going to allow the shaft to free spin. So depending on the specific application, you may want to configure your motor for coast mode or brake mode. So I think, for example, the azimuth motors on the swerve drive are set to brake so that they don't drift too badly, whereas the shooter wheels are set to coast so that when we stop applying a signal to the shooter motors, they don't try to immediately stop and hurt themselves. And of course, there are all sorts of different configuration options that you have for each individual device. And in general, you set all those different configuration options in Begin right after you do the open statement. Are there any questions about how you would go about opening a device or configuring a device? Okay. So we'll move out of the Begin CI for a second, and we're going to jump to the end. So if you see that there is, one of the cases is called finish. And the thing that I'll sort of point out is if we were to be connected to the robot and we hit the run arrow, you don't want to stop the code ever by clicking the stop sign. The way you'd want to stop the code if it is running on the robot is by clicking the finish button. The difference is if you click the stop sign, the code just stops. It just stops exactly where it is. Whereas if you click the finish button, the code can do some cleanup work and make sure that all the devices are disconnected from the RoboRio before it finishes, before the code stops. And this prevents issues with, the next time that you try to deploy code to the robot, are we going to have communication problems with the different devices? And so if we go into finish, what we see are a refnum name, a get refnum block, and then a close block. So if we wanted to duplicate this behavior for the Talon that we added, we would pull a refnum get. We would type in the name, which I believe was Talon 1. And then we would also need the close statement for Talon. And it's a bit odd, but if I remember correctly, there is no close statement specific to Talons. Instead, you have to go up a level and go to actuators, motor control, and then just get a sort of a generic motor close block, which is a bit strange, but that's how it's set up right now. And then you can connect to line. And that way, so what happens is when you click the finish button, it'll execute this. Because this is that flat sequence that makes sure that each frame happens first, it'll go ahead and make sure that all of these close statements are done. And then it will run the stop command. And this stop command is identical to the abort button right here. And so essentially clicking finish is going to exit out of the connections to all of your devices, and then it will press the abort button for you and close out the code. Are there any questions on how you need to finish the code or how you need to close out the references to all of your different devices? Oh, Amelia's had a question here. What constitutes something as a device? Does that include motor controllers, sensors, etc.? Awesome question. So a device is a lot of different things. It includes joysticks, sensors, any sort of actuator. So that could be motors, servos, relays, pneumatic solenoids, the compressors of device, any of those. Typically, cameras aren't considered devices, and the PDP is also not usually considered a device. But pretty much all the other control system components, certainly everything that moves in every sensor is considered a device. Does that answer that question, Amelia? Any other questions about devices or how to finish them or close the references? Okay. So now that we've opened and been able to close the devices, let's look at how we actually control them. So first, drive code. This project comes with default drive code, which is placed in the teleop enabled case structure. And so if we enter the teleop block, what they've got set up for us is the following. They have, first they get the reference lines for the motors and also the drive motors and also for the joystick. And the first thing that they do is they grab this block called get joystick values. And get joystick values has 3 arrays that come out of it. It's got axes, which are all of the joysticks on the joystick, as well as the 2 trigger buttons that have like that range of motion, the bottom trigger buttons are all tied together in this array. Then there's an array of Boolean values, and that's all of the buttons. So all of the buttons except for the triggers on the bottom are packaged into this array. And then the blue array that's here, the POV array, that is the set of buttons that the D-pad or the, I forget what else it's called. It's like called like a million different things. The D-pad, the POV, I think there's another one. It's the circle button with like you can click it in like a couple of different directions on the left side of the stick. And those are all packaged into the POV array. What they've done here is they've taken a index array block and they're pulling out the first 2 joystick values. So this is an array, just like we looked at yesterday, and they're pulling out those first 2 joystick values. And they are putting that into, they are putting that into the arcade drive block. And that's kind of a weird way to do it. I haven't really looked at that. That's strange. Okay. They are looking at, they are plugging into the arcade drive block, which is going to convert the 2 different joystick values into motor commands for the left and right sides of the robot. So in arcade drive, I think, if you press forward on the Y stick, both motors go at full speed, and then the amount that you press on the X stick slows down or speeds up one of the sides, and so that allows you to turn. And so it's going to convert those 2 joystick values into the command values for each side of the robot. Last year, we used our own custom version of arcade drive that we called Wild Drive, which gives us a lot more tuning parameters. And then obviously this year we're using Swerve Drive, so we're doing a lot more complicated math to convert the joystick values into commands for each individual motor. But first provide some basic values. This block right here, we haven't really talked about it. It's sending the data or storing the data for the left and right side motor values in what's called a network table. And the way I want you to think about a network table is it is a bucket that anyone on the internet network, like the local network for the robot, so that would include the RoboRio, the radio, the LimeLight camera, the driver station laptop, anything that's on that network can see that bucket, and it can also put stuff into the bucket and take stuff out of the bucket. And so if we want to share information between those Ethernet devices, internet devices, we use network tables typically. And so this one is storing the left and right motor commands to the network table. One of the reasons that it is doing that is the default dashboard code that FIRST provides shows a plot with the left and right motor speed. So this allows the two default pieces of code from FIRST to talk to each other. Are there any questions about this portion here? Okay. So at this stage, we've done the math for how we want to control the robot, and we've sent the results of that math to the network tables for the dashboard computer to be able to see them, but we haven't actually sent any commands to the robot itself. So the robot's still not moving at all. And so while FIRST by default does all of the math inside of all the math and all the decision making inside the case structures, if I remember correctly, they still send all the commands in this time to tasks block, which very confusingly, the default name on the icon is timed tasks, and the default name of the actual file is called periodic tasks. So you can blame Phil Malone from Team 1629 for that. They have not fixed that in the last 12 years. So that bug's been there. All right. Oh, and they haven't done it here. Okay, that's fine. Okay. Huh. So inside time tasks are a whole set of loops. You can have as many as you want. We can talk some more later about why you'd want to have fewer or more of them. And at the very least, what you should be using periodic tasks for is sending commands to your different devices on your robot, whether that's motors or getting information back, like getting information back from sensors. What I don't see here is, at least unless I'm missing something, FIRST doesn't actually seem to be sending the information to the drive motors. So I don't think the robot would actually move by default. Amelie is actually the last person who used the default code. I don't know if she's on the line and can mention whether or not she had to type in her own code to get that robot running at Little Rock. Amelie, are you there?
Yeah, I don't remember what I did.
Okay, that's fine. Yeah, I don't remember if there's something hidden in here that sends the commands to the drive motors. I don't see it anywhere, so I don't think it would work by default without doing anything different. So let's assume that it's not working right now, and I'll show you guys how you would do it inside of periodic tasks. So we can go back to, I already have it open. We can go back to WPI Robotics Library. And I just want to look real quick here. So the other thing that we don't normally use, unfortunately, is one of the things that we don't normally use is these default drive blocks. So I'm not overly familiar with them. We tend to control each motor completely individually because it allows us to do more complicated things. So I'll show an example with the Talon motor that we just added. So say we wanted to control the Talon motor. The way that we do that, and I know we're getting close to the end of the hour, I think the next section will actually take a little bit less than an hour, so I'm going to go ahead and finish out the robot project stuff, and then once we're done with that, we'll switch over to the next topic. So let's do the following here. So before we send the commands, let's go back and make a decision about how we actually want to command the Talon motor. So an option that we have is I'm just going to take the next joystick axis. So this is axis 0 and 1. I'm going to go ahead and grab axis 2. And I'm going to say that we're just going to directly map that joystick axis to the power that we want to send to the motor. Now, we have a bit of a problem in that this joystick information is located here inside of the teleop sub-VI, and where we're going to send the commands from is inside the periodic tasks sub-VI. And so we need a way to share values between those two pieces of code. And the way we're going to do that, and this is the fundamental difference between the two different architecture types that were at the very beginning, the way that we do that is with global variables. And so a global variable you can get to by going to the structures palette and then clicking global variable. And this is a variable that is, so a local variable would only, which we played around with a little bit, is only accessible and readable from inside of the same sub-VI. If you try and access it from another sub-VI, it's not going to be able to share information. The global variable is accessible by any VI that is in the project. And the way that you create a new one is you drop the global variable on, and then you actually have to double click on it, and you open up what looks like a front panel. The difference is there is no, if you hit Control E, there is no block diagram for this. So you only have a front panel for the global variables. First thing you should do is go ahead and go to File, Save As, and we're going to call this global variable outputs. One of the naming conventions that we have is that we do all lowercase for global variables, and we start with an uppercase for sub-VIs because they both have a .vi file extension. So if you're just looking in a folder, it can be kind of hard to differentiate which one's a global variable and which one's a sub-VI. So that naming convention allows us to identify that. You want to make sure, it's really important that you're saving your global variable inside of the project folder. And so we are. So if we're inside of the default robot project folder. So now you can go ahead and click OK. And then now you need to set the data type for the global variable. And so what you're going to do is you're going to right click, and you have a palette just like you would if you're on the front panel. And we can go ahead and put in, say, a control, or our convention is an indicator just because it really does not matter whether you use a control or an indicator for this at all. Our convention for using the indicator is just that the indicators tend to be a little tiny bit smaller and a little bit simpler, and so they're just a little bit easier to use. So we'll call this Talon 1 speed. And the other thing I want to point out real quick is that the global variable can have multiple variables inside of it, and I'll show you how that works in a second. But so we could also have, I don't know, we'll just call it Talon 2 speed, even though we don't have a Talon number 2. Are there any questions on creating the global variable yet? There's still more to learn with the global variable. Are there any questions on creating it? Okay. So the next thing that we need to do is make sure that the global variable has been added to the project. So we can go ahead and close this and go back to the project window, and you can see that outputs has shown up in the Project Explorer. Depending on how you create the global variable, that's not always the case. So if the output sub-VI, if the output's global variable had not shown up, what you need to do is add it to the project. So you would go to the target, you would right click on it and say add file, and then navigate to your folder. And again, you should only ever add files that exist in this folder. You should never like go out here and add a file from a different folder. So what we would do is we'd go in here and we would click outputs, and then we would say add file. It's already in there, so we don't have to do that. We hit cancel. The other thing that we can do is if we've got a whole bunch of global variables, sometimes that can start to get kind of cluttered if they're all on this list. So you can also right click on this and say new virtual folder and create a little, what's called a virtual folder for just the global variables. And then you can drag the global variables into that folder. And that's just a nice way to sort of keep the code organized. The other thing that you can do is you can right click on this and say, you have to remember, arrange by name. Oops. I don't know why. It should have dropped this below lib, but it did not. Sometimes it's not set up by arrange by name, and so it can be kind of strange to like keep track of where stuff ends up. Okay, so we've already got a global variable here. Because we created it this way, you can automatically click this and see this drop down and select one of these. And so now we can take this joystick value and we can store it in that global variable. One of the things that you need to be really, really careful about with global variables is you should never have more than one. You have to be very careful that you never write to a global variable in more than one location in your code. Or more explicitly, you should never write to the same global variable simultaneously in more than write to it simultaneously in more than one location. And so my general suggestion is that you just never place more than one global variable write for that global variable anywhere in your code. Now we do have some exceptions to that rule. There's one global variable in this year's code that does have multiple write locations. And that has to do with how we reset the robot position on the field. And we have to be really, really careful that we don't ever set it simultaneously. And it's sort of annoying. I don't really like that solution. That was the solution we came up with. But in general, we try to avoid having more than one write anywhere in the code. The other thing I'll point out is if you've already created the global variable and you want to put it in your code, the way that you can do that is you can literally go here and then just drag it on your block diagram and it will show up. Also, if you want to add more items to the dropdown, you can either double click on the global variable or you can right click on it and say open front panel. And you can add more items to the global variable. Are there any questions on writing a value to a global variable? Okay. So now that we've written the value to the global variable, we can now read it in periodic tasks and use that to set the commands for the motors. So if we go back to periodic tasks, we can go ahead and drag in our outputs global variable. Right now it is set to write. We need to right click on it and say change to read so that we're reading the value that's stored instead of writing the value that's stored. And then we need the blocks that allow us to actually send this information to the Talon. And so if we go back up to, if we go back to the WPI library, for Talon, we first need to get our reference number. So we need to remember our name again. So that was Talon 1. And then we have a set output block. And that requires us to put in our reference. And then it also requires us to put in the value that we're setting. And so every time this loop loops, so once every 100 milliseconds, we're going to send the current value that's stored in the global variable to the speed controller, in this case over the CAN bus. And so that's how we're going to get the information from the joystick to the individual Talon motor controller. Are there any questions with this portion? Let's see. Is Alex on the line? Oh, she is. So Alex, here's a question for you. Are there any problems with sending data to the CAN bus every 100 milliseconds?
Is that working?
It's working, I can hear you.
Is it gonna like make it have too much data?
Yeah, it
Like
can.
slow everything down?
Yeah, it can. So the CAN bus has a certain amount of data that it can have on it at any given time. So there's a certain amount of bandwidth. And if you send the commands over and over again, you can use up all the bandwidth and start to get lag between your controllers. That's one of the issues that the other architecture type solves. It only sends data when data change. We've solved that problem on our end, and it's there's a session that people have voted for that will cover this. We've solved it by having another structure around this block that checks to see when this value changes and only sends new values to the CAN bus when that value changes. And so that's how we reduce our CAN bus utilization. That's pretty much all I wanted to cover with respect to sort of the default robot code and how you send values from a joystick to the robot. I don't want to go too much more in depth with this architecture just because it is a bit different from how we actually do it. So I'd like to do more things with our architecture rather than diving really deep into the default architecture. But are there any questions on what we covered so far before we move on to the sensor fusion part? Okay. So the sensor fusion part is going to be a lot more interactive. I'm counting on all of you to help me build the sensor fusion algorithm. So I'll start with talking a bit about sensor fusion and why we need it, and then we'll use what we learned about arrays and for loops in order to create a sensor fusion between the LiDAR data, which we don't have yet, but we can pretend that we have it, and the distance calculation that we have from the wheel encoders. So let's see. Okay. Okay. So does someone want to give a definition of what they think sensor fusion means and why we might use sensor fusion and need it? So I see Amelie, I see Alex, I see Amelia, I see a number of people on here. I can answer that question.
Okay, so sensor fusion is like using a bunch of different sensors to get a more accurate reading.
Okay. Yep. And then Michael and Juliana also answer that. So, and Alex did as well. So the essence of sensor fusion is that, you know, sort of the assumption that you make is that each sensor that you have on the robot is unreliable. There's different problems with different sensors, and they all have different amounts of error. And one of the ways that you can reduce the impact of that error on how the robot behaves is combining data from different sensor types and essentially averaging them together in an intelligent way, so that the final estimate is improved. So a really simple sensor fusion would be, you know, if we had two infrared range finders, we could point them both at a wall, and if we just straight up averaged those two values together and use the average value, that would count as sensor fusion. That is a, you know, sort of the simplest sensor fusion you can have is averaging the values from duplicates of the same sensor looking at the same thing. Where sensor fusion can get Yeah, so Amelia asked, would the pigeon be an example of sensor fusion because it uses multiple gyros? Absolutely. So the pigeon has, I believe, 3 gyroscopes per direction. So there's or 2 gyroscopes per direction, maybe, because I think there's a total of 6 gyroscopes. So 2 for the X, 2 for the Y, and 2 for the Z. And there's a compass, and there's a temperature sensor. And it uses all of that information and averages them together in order to improve its estimate of its angle. And so in particular, what it tries to do is it uses the gyroscopes to get the very fine detail of how much the robot has rotated. But the gyroscopes have a problem where they tend to drift. Anyone who's in LEGO League and uses those gyroscopes know that you get, as the robot's just sitting there, the gyroscope tends to wander around. And Alex says she hates the gyro sensor. So it can use the gyroscopes for these very fine changes and then use the compass in order to know that the robot's not actually drifting, like it's not actually moving, and remove that drift. One of the problems that we ran into this year is that at Bilo Largo, we can't use the compass. The building is a steel-walled building, and so it screws with the compass, and so we had to turn the compass off. And so that's why we do still get some gyroscope drift. Now, the other thing that the pigeon has on it is a temperature sensor. Now, the temperature sensor does not directly measure the rotation of the robot in any way. What it does do is part of the gyro drift comes from how the gyroscope behaves under different temperature conditions. And so if you know the temperature, and if you know how the gyroscope behaves, which is what we do when we do the temperature calibration, you can correct for some of the gyroscope drift by fusing that information in there too. So that's why when we turned on the temperature calibration, a lot of our gyroscope drift problems went away. There's another little nuance there. Doing the temperature calibration on the IMUs improves the accuracy even if that particular IMU isn't affected by temperature. The reason for that is there is a periodic calibration that the robot runs on the IMU, but it's only enabled if the calibration has been run once. And so the live, constantly updating calibration that looks for acceleration and tries to get rid of the gyroscope drift doesn't run until you've run the calibration. So there's some other nuances as to why that running that calibration fixed it, but that's sort of the main reason. Does anyone have any other questions about the IMU and how it handles the different sensor data? Oh, Amelia's typing, I think. Oh, yeah, they visit me really regularly, so the police come all the time. It's fine. Don't worry about it. Okay. So another example of where we're using sensor fusion explicitly in the robot code is for calculating our angle to the target. And there's a couple of issues that we're using sensor fusion to address. So first, I guess I should say we have 2 ways to measure the angle to the target. The easy and most accurate way to measure the angle to the target is by using the LimeLight camera and looking at where the target is within the field of view of the LimeLight camera. The second way that we can calculate the angle of the target is if we're constantly tracking our location on the field and the target is always in a fixed location, we can use trigonometry, sine and cosine, in order to calculate the angle to the target at any given location. The advantage of calculating the angle that way is we can calculate an angle even if we can't see the target. So we then know the angle to the target even if we're pointing in the opposite direction, or if another robot is blocking our view to the target and we can't see it with the camera. And so that allows us to start the auto-targeting mode even under those situations. The disadvantage is it's not very accurate because our robot's location information can be off by, it could be off by as much as a couple of feet. We've even seen it off by 12 feet or more, depending on what we're doing and in different cases. And so that angle estimate is not very good. And so what we really want to do is combine the estimate from the robot position with the estimate from the camera and use that fused value in order to make our decisions. And I don't want to show you the code yet for that because I want you guys to think about how we would do this in this next scenario first. And so this next scenario is the LiDAR system, where we're in a very similar situation. We're going to have two ways to calculate the distance to the target. We have the way that we've been doing it exclusively, which is by estimating our location on the field and using the Pythagorean theorem to calculate the distance from our guessed location to the target. We know that that is not super accurate, and that was part of the problems that we were running into at Little Rock. And what we're going to have is a new way to calculate our location, our distance to target, which is the LIDAR Range Finder. The problems and the advantages are very similar. The LIDAR Range Finder is only going to be giving, it's always giving us a distance, right? It's always measuring a value of something, right? The robot is always some distance away from whatever it's pointing at, but it's not always pointing at the target. And so that value for the distance from the LiDAR is not always reasonable or correct. And so we need a way to combine those pieces of information in an intelligent manner. And we will still want to have sort of the same capabilities that we had before, where we can start spinning up the, right now, things may change with the new CAL design, but right now, the shooter spins up to a different speed based off of its distance from the target. We would like it to start spinning up to approximately the correct speed as soon as we enter auto targeting mode, even if we aren't facing the target. So that initial spin up might be based off of the distance estimate from the robot location, and then the final speed, target speed for the real shooter is going to be based off of the LiDAR information. And so we need a way to combine that. And so I'm going to go ahead and open up a blank CI here. And we'll call this one LiDAR Sensor Fusion. Okay. And I'm going to go ahead and create two controls. One that is the LiDAR range in inches, and the other one is the estimated range in inches. So this is the range based off of the Pythagorean theorem estimated from the robot's location. And we're just going to assume that we have both of those sensor values and they've already been calculated for us. Okay. Okay. So does anyone want to talk about, so Michael was asking, are we not going to use the LimeLight? So we're not going to use the LimeLight for distance calculations. We did attempt initially to use the LimeLight to calculate the distance. Unfortunately, we found that those estimates were not very accurate. There was a lot of noise in those values. There are ways to improve that by doing it a different way than we've done it before, looking at a different portion of the target, but it's still not going to be as robust as the LiDAR. And so we're going to go ahead and jump to the LiDAR And if we need even more reliability, we could look at doing a sensor fusion between 3 sensors, one being the estimated range, one being the LIDAR range, and the other one being the LimeLight range. So, but for now, we'll start with just the estimated range and the LIDAR range. So, does anyone want to propose an option for fusing these 2 values together? And actually, here what I'll do is I will create an indicator, which is the fused range in inches. Right. So who has a thought?
You could average them.
Okay. So we could average them, certainly. Okay. And I need a divide. Okay, so is this what you were thinking, Alex?
Yep.
Okay. So someone's already posted in the chat a potential solution. But does someone want to say what might be a problem with averaging them in this way? So Amelia says one of them is more reliable than the other. So that's absolutely correct. So we know the estimated range is less accurate than the LiDAR range. And so one of the things that's pretty common is to trust different sensors different amounts. And so Gianna and Michael have posted that what if we used a weighted average? And so that's certainly something that we can do. So a weighted average is, best way I can think about it is we could sort of copy these values, right? So if we took, I'll show you a better way to do it in a second, but just to sort of explain things. If I replace this with this block here, it's called a compound arithmetic. It allows us to add more than 2 things together at once, which is kind of nice. It's just a convenient way. They're all just being added together. It's just convenient. One thing that we could do is basically count the vote from the LiDAR rangefinder more times, right? And so now we've got a total of 4 values, and 3 of the values are from the LiDAR rangefinder, and 2 of them, and only 1 of them is from the estimated range. So we're trusting the LiDAR 3 times more than our estimated range. Does that make sense to everyone? Okay. So there's a cleaner way to do this than just sort of running the wires over and over again. So your other option is you can multiply your values, by different things. Different factors. So we could multiply the estimated range by 1 and add that in, and then we can multiply the LiDAR by 3 and add that in. And then if we wanted to get really clever, so we didn't have to keep tweaking that that value there, I'm sorry, we could go ahead and sum these weights together so that the denominator is always correct. So like we can go here and just tweak this and not have to remember to tweak the denominator over here. Does this way of doing the weighted average make sense? Okay. So where could you see a problem still arising if we do this? Is the LiDAR range finder always more reliable than the estimated range?
No.
So when is it not always, when is it not more reliable?
When it's not pointed at the correct thing.
Okay, so absolutely. So what should we be trusting when we're not pointed at the correct thing?
The estimated, dude.
Yep. So what we can do is what's called a dynamic trust factor. There's lots of different ways to do that. It could be a function. It could, so here we'll start with the simple one. So if we just have, we'll start with the simple one and we'll go to the more complicated one. If we have just a value that we've determined via some other way, it says pointed at target, and for this one we would probably use the LimeLight to know this. What we can do is set this over here, and then we can take a select block. And when we're pointed at the target, our trust for the LiDAR will be a 6. But when we're not pointed at the target, our trust for the LiDAR will be a 0. And so the weighted average will now only be based off of the estimated range and will have no component from the LiDAR in it, because we're not looking at the target with the LiDAR, so it doesn't make sense to incorporate the LiDAR information. Does that make sense to everyone? This doesn't have to be an on-off decision. You know, we could, depending on the sensor type, we could be more or less confident about whether or not we're pointing at the target, and we could have some function where when we're really confident that we're pointing at the target, the value is 6, and when we're really not confident that we're pointing at the target, it's a 0, but if we're like kind of confident that we're pointing at the target, then it's a 3. So depending on your specific application, you could design a function that dynamically changes how much you trust the different sensor values with respect to each other based on other conditions. Does that make sense? Okay. Okay, so we've solved that problem perhaps. What is another issue that you could see happening?
What if they're both really, really wrong?
Okay. If they're both really, really wrong, you're not screwed. There is a way that we can talk about that. Let's hold that, because that'll actually be the second, or I guess the third issue that we'll talk about. There's another one that's similar. What if one of them is really, really wrong, but we don't know it? And I guess it's related. It's going to have the same solution as to the problem that Alex just suggested.
Do we need to compare them to each other? And if they're like outside a range, or they're like an outlier to something, then we need to get rid of them?
Yeah, we can certainly do that. So that's a really good idea. So actually, that's another solution I'd forgotten about. So let's go ahead and show that. Me. Yes, 1 point for you. So I forgot about that solution. We are using that solution on the calculation for the robot position on the field. So if the value from the wheel encoders is very, very different from the value that we're getting from the LimeLight, we, I think, don't trust the LimeLight at all. And so Alex's thought here is that, well, here, I'll ask you, Alex, if it was your idea, how would we incorporate that check into this code?
Do we need to use like like a max and a min that you were showing us earlier with the array thing.
A max and a min in the array palette.
No, it was maybe in the comparison. Yeah, the
So
max.
we got the max and the min here. Okay, so what am I doing with the max and the min?
I don't know. I hadn't gotten that far. I was hoping you could put it into like something, and then it would tell you if it's like within, if they're like close by like a number.
So how about we start with, how would you calculate how different they are from each other?
Good old subtraction.
Okay. We'll grab a subtraction. Okay. Is that all we need on the subtraction?
No, we need an
We just
absolute value.
Okay, so why do we need the absolute value?
Because if we get a negative number, then it might screw up stuff.
Okay, perfect. So the absolute value gives us just the error between these two, and we don't have to worry about whether it's positive or negative. So typically when we're looking at this kind of thing, we're going to end up using absolute value. Okay, what next?
Wait, my computer's dying. Let me go run and find the charger. But you need to figure out if the number is like less than the whatever we want the error range to be.
Okay, so while Alex is going to get her charger, does someone know where we can find the less than or the greater than signs? Okay, comparison. Amelia says comparison palette. So let's grab the the greater than sign. So we'll ask the question, when this error, I'll call it difference or disagreement maybe. Ask the question when that disagreement is greater than, I'm trying to give some more space here, is greater than some value. We'll say 100 inches. So I'll just make sure that everyone knows that that's in inches. Okay. So what do we want to do if the error is greater than 100 inches? What should our choice be, or our decision be?
Between the 0 and the 6.
So if these two, well, so let's step back a second. So if the estimated range and the LIDAR range are very different from each other, we can assume that one of them, that there's the possibility that they're both wrong. And then there's also the possibility that only one of them is wrong. Let's not worry about them both being wrong right now. Let's just assume that one of them is wrong. Based on physically how they work, which one do you think is more likely to be very wrong all of a sudden?
The estimated one?
So how come?
Well, if the LimeLight or the odometry gets off. But aren't we already checking if we're putting out the target for LIDAR, so it wouldn't be the LIDAR?
So what if, so you're right that the odometry could normally get off. I will say that the thing that usually makes the odometry all of a sudden be very, very wrong is if it gets a bad LimeLight signal. And we are actually already doing this exact kind of check for the estimate position. So there's another one of these disagreement checks embedded in this one. With the LIDAR, what I would be worried about is, depending on exactly where it is on the robot, and maybe it's not a problem at all, and you'll have to just see. You could imagine a scenario where the LimeLight is able to see the camera or see the target, but another robot could drive in front of us and block the LIDAR. And so all of a sudden the LiDAR range would be very wrong, but we'd still be pointing at the target, for example, or a ball flies in the way. Now, if we're very careful about how we mount it, we may be able to immediately know when we can't see the LiDAR because the LimeLight will go out. And that would change our decision-making process, right? There's not like a fixed right answer to this question. We have to evaluate with real data and with how the robot actually performs, which sensor we should trust more. And in certain situations, this may be different. I mean, you know, if we had, for example, another an IR range finder that told us if a robot was close, then we could use that to incorporate our decision about whether or not to trust one sensor more than the other. So we could add sensors or intelligence to the robot in order to make this decision even better. Again, there's not really a right answer. It's always a guess. And you're just looking at what is the most common failure point in order to, at a given situation with the information that you have, in order to guess which sensor is wrong. On spacecraft, what they typically do is a vote of 2. So there'll be 3 identical sensors for every single sensor that's on that spacecraft. And if one of them disagrees with the other 2, you go with the 2 and assume the third one's wrong. We typically don't do that because we don't have enough money or the need to have that kind of redundancy, but that's one of the approaches that people do, is put a lot of identical sensors on and vote between them. Okay, so let's proceed. Are there any questions with that sort of nebulous answer for which one we should trust more in this situation? Okay, so assuming that we're going to trust the LiDAR, or sorry, the estimated range over the LiDAR in the situation where we have this big disagreement, what's the next thing that we should do?
Shouldn't we switch the 0 and the 6? Because if the disagreement is true, then we want it to be not trusted. But if it isn't true, then it is trusted. Okay,
we could switch that. What else could we do to this in order to do the switch without having to switch the 6 and the 0?
Not.
Okay, yeah, let's do that. Let's just try that way. We don't have to change the pointing to target value. So if we go ahead and get a not, okay? And then now how do we combine? Because we want it to happen either when the disagreement, we want to not trust this, either when the disagreement is large or when we're not pointing at the target. So what else do we need? Say it again, Alex. Sorry, I missed that. Oh, you really put it in an or. Okay. Actually, Amelie answered. Okay. So let's go ahead and put in an or. Okay. So now we have a reasonable solution for how to handle a disagreement between the 2 sensors and how to handle which one we trust more than the other. So let's go back to Alex's concern about what if both of them are wrong. If we think about what we did yesterday, what might be a solution to the situation where both of them are very wrong? So on Tuesday, we were also looking at issues where the sensor values weren't stable. And what did we do?
We did that thing where it went to 0.
Went to 0. Okay, so we did have like a bound on there so that if it was a value that we knew it couldn't exist, we removed it. You can sort of think of that as, you know, we could add another restriction here, like if the LiDAR value is negative and we know there can't be something behind the robot, we would also put in an or, we also trigger it to not trust the LiDAR instead, for example. So that'd be an option if we have a physical limit on our system that we know we can't actually exceed. What else did we do on Tuesday?
Averaging over time.
Exactly. So if we average over time, we can mitigate the influence of a very wrong value on both of the sensors and reduce the impact that that has on how the robot behaves to that signal. So in order to do that, we're going to need a while loop. So I'm just going to go ahead and make one around this whole thing. And while I'm doing that, I'm going to clean this up a little bit. Start thinking about how we're going to do the moving average. So I'm just going to clean this up a second. All right. Oops. Okay. All right. So what, let's see how I want to do this. Oh, this is kind of interesting. So we can actually do this in a little bit of a simpler way than I was initially thinking. I'll show you why I was initially thinking I'd do it more complicated, because we did for the other algorithm. But in this case, we don't really need to do anything super complicated. So we can probably just apply the moving average directly to this value here. So want to guide me through doing the moving average on this value?
Do we want to initialize an array and then we like take the value every time it does stuff?
Okay, so initialize an array. So we got initialize the array. Right. Again, we'll sort of just fill it with zeros. There's some more robust ways to handle that, and I'll show an example of that in a second. But we'll actually here, I'll just show the robust way of doing it now. So instead of doing it with shift registers around the outside, we'll use a feedback node this time. So we did it before with shift registers on Tuesday. We'll do it with a feedback node here. So we could initialize the array with that very first value that we get. So at least it's not a zero. It's the best guess that we have at any time. Let's average over the same number of loop cycles that we did before, just for fun. We'll do 10. Okay. So what do I need next, Alex? Or anyone?
You need to build the array with the value and then like replace it, or whatever the block was that we had to change something because we
did it wrong. Yeah. So the replace. Okay. So we've got the array. How are we going to know what index to replace?
The counter thingy.
Okay. I think that will be fine. That's fine for this because we're just going to do an average. So I was just making sure. So what do I need for that?
The quotation and remainder block.
Okay. Oops. Need a little I. So that's our iteration counter. Oops. And we'll use the remainder to be our index. We're going to replace it with that value. What are we doing to the output of this in order to get the moving average value? Okay, Michael and Juliana say summing, and then dividing by 10. So we'll go back to the array palette. We'll go ahead and, I think there's a sum in here. Oh no, numeric palette, there's add array elements here. And then a divide by 10. And so that is now the value that we would put out there. Anyone want to refresh your memories on how we get rid of the red error on the divide symbol? And Amelie says convert to double. So we right click on it and we say insert numeric palette conversion double. Okay, and then what else are we missing? So what else do we need in order to get this to work? How about we need to remember what our previous values were, right?
Yeah.
Okay, so what are we going to use? We're going to use the feedback node, is what we decided, right?
Yay.
Okay, so we'll grab a feedback node. I'm just going to stick it up here. It's going to be kind of ugly. This line that we kind of just threw in there, that actually is what we're using to initialize the feedback node. And then that gets plugged into, I'm sorry, this is kind of a nightmare of wires, so I apologize. And then the array with the newly replaced value goes back into the feedback node. And then this is the moving average. So what we have here is an example of taking in two sensor values, trusting them different amounts, handling cases where one of them disagrees very strongly with the other one, and then also applying the moving average that we did on Tuesday in order to mitigate any problems with both of the values being very wrong. Are there any questions with this before I go through how we did it for the camera angle, which is going to be a little bit more complicated than this approach? Okay, so does anyone have any thoughts on why doing it for the camera angle is going to be more complicated than doing it for the LiDAR? Sorry, Michael and Juliana asked, won't our values change very suddenly because we dynamically add in another sensor? So why use the moving average? Can you ask that question again? I'm not sure that I understand that one. Okay. Okay, well, if you think of another one, just let me know. So does anyone have any thoughts on why doing this for the camera, like the angle to the target, is more challenging than doing it for the distance calculation?
Is our angle changing faster?
I wouldn't say it's necessarily changing faster. And I'll also say there's actually two unique differences. So what's the difference between a distance value and an angle value? What is an angle? Anyone who maybe worked on some of the Swerve code, or any of the Swerve code or any of the turret code, what's one of the annoying things about working with angles instead of just like distance numbers? Yeah, they wrap. So Michael and Juliana said they wrap. So since they can go anywhere from, as they increase, right, they go from 0 to 360 and then back to 0 again. Averaging together two different angle readings can be a real problem. So if I have an angle reading of 359 degrees and 1 degree, if I do that average, right, that's 359 plus 1 divided by 2, which is 180 degrees. Is that correct? What should the answer be? Yeah, 360 degrees or 0 degrees. So that's one thing that we have to deal with, is how do we average together these values when they wrap. And then the second problem is a little bit harder to get your head around. But for the LiDAR system, the values from both sensors are measuring the same thing. So they're both measuring the absolute distance between the target and the robot. For the angle measurements, the estimated angle is measuring the angle from the direction that is forward down the field, so like absolute 0 degrees, and the target position. Whereas the angle that's on the camera is measuring the angle from the center of the robot to the current location of the target. And so they're not the same angular measurement. One of them, the camera angle, is completely dependent upon the rotation angle of the robot. And the other one doesn't care whether the robot's angled or not. And just so we know, because Adam's on the line, when we add the turret, the camera angle is now dependent upon the robot's angular direction and the turret's angular direction and the location of the target. And so that's one of the reasons that as we add the turret, we sort of have to revisit some of this code. So let me pull up the way that we handled the sensor fusion. And I don't know how many of you have actually been able to see this before. This was the one that I had to write like on the plane flight to San Diego. And it was done that way so that we would have it ready for that following weekend, because we were running into a lot of problems. So I made a simplified version of it last night, so there's not as many things going on. So this is not all of the code, but most of it. And what we have are 4 inputs now. We have the estimated heading to target, which is based off of the robot location and cosine and sine of the angle. We have the angle coming from the LimeLight camera. We have whether or not we can trust the LimeLight camera. Now in the real code, this is an OR statement with a whole bunch of different values, but right now, just for simplicity's case, this is just a true or false saying, yes, we can trust the LimeLight, or no, we can't trust the LimeLight. And then because the LimeLight angle, like the true conversion between the LimeLight angle and this type of angle is dependent upon the robot's angle, we also need to include that. Now, the other sort of wacky thing that's going on here is, I'm trying to think if there was a better way to do this, and there may have been. And I've got to try and remember. Okay, yeah, so that's the other sort of weird thing. And I'll have to think about, I apologize, I should have thought about this more. I'll have to think about this more with the LiDAR and whether or not it matters as much for the LiDAR. I don't think it does, but we'll need to check. So the other thing that's going on here is if we look at the averaged values, and I guess I should say this does actually apply to the LiDAR, so we may go back and do this for LiDAR in another session. We're averaging over a set of time, and some of those values are old. As we rotate the robot, we know that we are no longer pointing in the same direction as we were before. And we know that from the IMU. And so if we're looking at values from the LimeLight in the past, it doesn't necessarily, like it's a sort of a baseline option is to just average them in. But those, we know that some of those average values are going to be wrong because we know that the robot is rotated. And so that angular measurement from the robot to the target is no longer accurate because the robot's true rotation has changed. And so what we end up having to do is we have to memorize the robot's location when we measured it with the camera, and then also adjust that for the amount that the robot's rotated with the IMU. And that, again, improves our total accuracy for how we're estimating the total angle. Does that, I'll talk about the solution in a second. Does that problem make sense? Or are there any questions about that problem? Okay, so the way we ended up solving this, or hoping to solve it, was we memorize in arrays 3 values. So we've got the number of loops that we're going to average things over, which was 15. And we've got 3 feedback nodes. One that's storing the camera measurement, like literally the measurement off the camera for the angle. And this angle is the angle relative to the center of the robot. So it has not been corrected yet for the position of the robot. We also memorize the robot's current direction based off of the IMU at that time. And we memorize whether or not we should be, and we memorize whether or not we should be trusting the estimated target position or the camera target position. One of the things that we are not memorizing is we're not memorizing the old estimated heading to target. We're only going to be using the estimated heading target that we have on the current time. And the reason for that is there are already averages going on with the robot pose calculations in order to smooth this value out. And so this value shouldn't be spurious, just like we trusted the estimated distance over the LiDAR distance. This value shouldn't change dramatically, so it should be pretty stable. Whereas with the LimeLight, we can be affected with different lighting conditions or a ball going in front of the target or any other things that could be causing problems. So we're going to take these memorized values, this array of memorized values, and we're going to go into a for loop, and we're going to use the auto-indexing tunnels. So there's 15 elements in this for loop. and we're going to cycle through all 15 of them in order to make decisions. And one of the things that I'm noticing now is we probably could have taken this stuff out of the for loop and done some of this. I guess we couldn't have done this before. I guess it does have to be in the for loop. I'll explain why in a second. If everything here was an array, like if we were saving the estimated heading to target, then we could do all these calculations here and then save them all together, basically save the answer. But we aren't quite able to do that because some of the values have to be the current value and can't be the ones from the past. And so what we're doing for each individual value here is we're going ahead and combining the robot heading and the LimeLight angle in order to get an angle that is relative to like the absolute zero angle on the field, and it's no longer relative to the rotation of the robot. So we're, with this addition and this modulus calculation, we're putting this angular estimate from the LimeLight in the same reference frame, in the same units as the angular estimate from the estimated target heading. Does this combination of the LimeLight angle with the robot heading to get sort of the absolute angle make sense to people? So we do that in a couple other places in the code, but it's also here. We're then remembering whether or not the LimeLight information was valid at that timestamp, right? So we've got, this is from 15, this may be from 15 timestamps ago, 15 loop cycles. So we've also got to remember whether 15 loop cycles ago the LimeLight was valid. And instead of doing an averaging, which we could do, we decided to not explicitly do a weighted average between the two of them. We just choose whether or not to use, whether we use the LimeLight value or the estimated target value. You can sort of think of, you know, that's not necessarily the best way and seem to work fine. Again, we're still doing an average because if we trust the LimeLight for more loop cycles than the estimated target, like over those 15, that also sort of acts as a weighted average because we're still averaging over the total, over those 15 loop cycles. That doesn't mean that we couldn't also include a dynamic trust factor and a weighted average here and maybe improve the results, but that's not what's in here right now. We then have to use this block, which I won't get into, but it essentially calculates the distance, the angular distance between the robot's current orientation and the target. And so it gets rid of the issue of the fact that you wrap from 0 to 360 degrees. It has all the math to handle that. Now, the interesting thing here, and the reason why this stuff has to be in the for loop, is that the angle that you need to use in order to compensate for, in order to calculate the robot's angular distance to the target has to be, or it is best if that angle is the robot's current angle from the IMU and not the angle from before. And the reason for that is we have this additional information. We know that the robot has moved, has moved angularly. We know that that has happened. And so we should incorporate that information into our fusion in order to improve our results. Does that make sense as far as why we want to use the robot's current angle? Or are there any questions with that? So sort of the difference between this and the LiDAR case is that encapsulated in both the LiDAR range and the distance to target estimate, we have that current robot location. There's not this additional piece of information that we're getting from an IMU about, you know, we don't have another, it's not, we don't have another sensor that's giving us information about how much we've moved closer to or from the target. all we have is the estimate and the LiDAR range. Whereas in this case, we have the estimate, the camera angle, and the knowledge from the IMU about how we've behaved in the interim period of time. So we then construct an array on the other side with the auto-indexing output tunnel. That will be the stack of, or the list of these distances to the target. Obviously, hopefully, I shouldn't say that, if we're in our target, I shouldn't say the distance should be decreasing through those ranges. There's some nuances there, but I'm going to hold off on that statement because I have to go back and think about whether or not that's true. But we're going to get the average, an estimate of how much distance we have to angularly turn in order to be pointed at the target. Does that portion make sense? Okay. So the last thing I sort of want to walk through here is how this behaves in real life. So if we're pointed completely away from the target, the LimeLight, so say for the last 15 loop cycles, we've been pointed completely away from the target. We're not going to trust the LimeLight values at all. And what we're going to do is our average is just going to be an average of the estimated headings to target. Now, with the estimated headings to target, because that has no memory, it's all the same value. So all 15 values in this array are the same one. And so we basically, you can almost think of it like if for the 15 loop cycles we didn't see the target at all, we're literally just using this value. That value is just connected straight to there. It's like just connected straight to there. And we're basically bypassing the LimeLight. We're bypassing the explicit averaging because there's other averaging that's going on before to make this estimate more robust. And we're just using that estimate. Any questions with that case, with that scenario? Okay, so let's imagine the other case where we've been pointed at the target the entire time for more than 15 loop cycles. So all of our values are based off of the LimeLight. So we now no longer have any of these estimates, which could be very wrong depending on how much the robot's position calculation is off. We're now only looking at the LimeLight values, which should be pretty robust. And they still got an average on them. So if there's any sort of spurious value that's very off, it gets averaged out. It's not as big of an impact. And so that's that other case, sort of the other extreme case. Now, the other situation you can imagine is as we start pointed away from the target and we start automatically spinning towards the target, all of a sudden the LimeLight comes into view. And that's where we start transitioning between the estimated angle to target and the LimeLight angle to target. And so as we go through those 15 loop cycles, we go from them all being based on the estimated angle to being the LimeLight angle. This has a couple of advantages. I mean, one, it allows us to continue averaging over the full range of time from the very beginning. So if we didn't do this, but we still wanted the average in the LimeLight, we wouldn't really have an average for the first 15 loop cycles, right? We'd have to wait some amount of time to be able to really have an average value. Whereas here we get the advantage of having an average value from the very beginning. The other advantage is that the angle measurement from the estimated angle measurement and the LimeLight angle measurement are not going to be the same. They're going to be different. This value, this fused heading target, is going into a PID controller. If we were to just immediately switch over from the estimated target to the estimated angle to the LimeLight angle, that PID would all of a sudden have a very different goal that it's trying to get to. And that can cause an instability in how we track on the target. Here, we do a smooth transition between the estimated angle and the LimeLight angle, and so we can smooth out that transition between those two values and improve the response of the PID. Does that use case make sense to everyone? Okay. And the last use case is if we are shooting the ball, or we're already pointing at the target, we've been pointing at the target, we've been using the LimeLight values, and something happens to the LimeLight, right? Another robot comes in front of us and disrupts the camera field of view, or a ball goes in front of us and you know, jiggles where we think the target is. We have a couple of options. You know, we could ignore that value and still doing a moving average on the LimeLight. You do run into a problem, and that could work. That, you know, remove that little issue. You then still have a little bit of a problem where if it goes on for, you know, say 10 loop cycles, now you're only averaging values over 5 loop cycles because you've sort of taken out 10 of them as not being usable. And so now you can start getting some weirdness in the values that you're reading. And so what this one does, what this one allows for, is we can still keep averaging over that whole time range, because what we're going to do is essentially on the frames, on the loop cycles where we don't have a valid camera data, we're going to backfill it with our estimated angle. And if it goes on for a long time, right, if that robot is sitting in front of us for a second and we've gone through the entire set, you know, or the entire moving average window, what we've essentially done is transition back to using the estimated angle. So that's not ideal, right? I mean, the estimated angle is more likely to be wrong than the camera, but if we can't see the target, it's really the best estimate that we have. You could, you know, so the only other alternative is to assume that the target is still at the same angle as it was the last time you saw it. The disadvantage with that is if the driver is moving the robot around a lot, that's definitely not true. And so we can at least sort of compensate, we can take into account the robot's motion while we're not seeing the camera if we sort of do the smooth transition back to the estimated angle. And then the last thing I sort of want to point out is that the bug that was in this code was exactly the bug that we discovered on Tuesday. I had put in, instead of replaces, I'd put in inserts here in these sort of 3 locations. Now, the code still worked because the for loop only went through the first 15 portions, first 15 indices, and those were the ones where we were putting the new values in. So it was working fine. Like it was doing the calculation correctly, we didn't notice it. The problem is that these 3 arrays, as the robot was turned on for longer, the list was getting longer and longer and longer and longer. We were growing the list by, you know, we're adding 3 numbers every 20 milliseconds for the entire length of time the robot was on. This is eventually going to fill up the memory on the robot. And I don't know that this is one of the reasons that we had some weird instabilities when we left the robot on for long periods of time, but it is possible that this was causing a problem like that. So we need to make sure we make that change to the code. Does that bug make sense to everyone and what the issues are? So that was what I wanted to talk about today. There's more theory today, and I know it's a little bit more complicated. Are there any questions that people have about the sensor fusion stuff that we covered in the last hour? Okay. Well, I'll